What if everything we know about comets is wrong? 3. iAtlas just proved it. This interstellar visitor is breaking physics, getting brighter as it moves away from the sun. That's thermodynamically impossible. Objects don't heat up when they move into colder regions. Yet multiple telescopes confirm it's real. NASA just issued a priority alert. Harvard can't explain it. And what scientists are witnessing right now might rewrite everything we thought we knew about how the universe works. This isn't speculation. This isn't theory. Observatories across 3 continents are measuring something that shouldn't exist. Hubble sees it. James Webb detects it. Ground-based telescopes in Chile, Spain, and Hawaii all confirm the same impossible result. A comet from another star system is violating fundamental principles that have been tested billions of times. Principles we've relied on for centuries. Principles that say heat flows from hot to cold, never the reverse. 3. iAtlas is ignoring those rules, and it gets stranger. The chemistry is inverted. 8 parts carbon dioxide to 1 part water, the opposite of every solar system comet. The dust polarizes light in directions that violate scattering theory. Brightness fluctuates with no pattern, no warning, no explanation. NASA's Planetary Science Division issued a formal statement acknowledging that existing models cannot explain what's being observed. When space agencies say that, it means the rulebook just got thrown out. This is why 3iAtlas matters, why the global astronomy community is scrambling, why every measurement adds mystery instead of clarity, and why this ancient traveler from beyond our solar system is forcing us to admit that our comprehensive understanding of comets was never comprehensive at all. Before the alerts, before NASA's statement, before anyone realized this comet would shatter expectations, there were hints, small anomalies that seemed explainable, until they multiplied into something undeniable. Mid-2025, Hawaii's Atlas survey detects a faint object moving through the constellation. The Asteroid Terrestrial Impact Last Alert System runs automated scans looking for near-Earth objects. Most detections are routine, known asteroids on characterized orbits. Occasionally something new appears. 3iAtlas looked routine initially, a faint moving object. Follow-up observations confirmed it was real. Orbital calculations began accumulating as more position measurements came in. Then the orbit calculation revealed something extraordinary. Hyperbolic trajectory, eccentricity greater than 1. The mathematical signature that means this object isn't bound to our Sunday. It came from interstellar space. It's passing through. And it will leave, never to return. The I designation was added. 3iAtlas. The third confirmed interstellar object in human history, after 1I Oumuamua in 2017 and 2I Borisov in 2019. Only 3 interstellar visitors ever detected and tracked, each one a cosmic messenger carrying physical samples from stellar environments we cannot reach. The astronomical community took immediate interest. Observation time allocated at major observatories, spectroscopic programs planned, imaging campaigns scheduled. Because interstellar objects are rare opportunities. They don't stay long. Once they fade, they're gone forever. Initial observations showed cometary activity. 3iAtlas wasn't an inert rock like Oumuamua. It had a coma. Material was being released from the nucleus. This was an active comet, sublimating ices as solar radiation heated its surface. But early spectroscopy revealed something unusual. The emission lines didn't match typical cometary spectra. Water signatures were weak. Carbon dioxide signatures were strong, very strong. Stronger than any solar system comet showed at comparable solar distances. This was the first hint that 3iAtlas was different. Not just different in origin, but different in fundamental composition. The ice mixture didn't match local comets. The chemistry was exotic. Brightness fluctuated unpredictably. Standard cometary brightness curves follow thermal response to solar heating, gradual changes correlating with solar distance. 3iAtlas showed rapid variations, short-term flares, sudden brightenings with no obvious trigger. The coma showed unusual color. Most comets appear greenish or reddish from molecular emissions. 3. I-Atlas occasionally glowed blue, intensely blue during perihelion passage. Blue indicates ionized carbon monoxide or specific carbon radicals. Finding that chemistry at observed intensities suggested carbon dominance over the water and dust that color typical comets. Then dust polarization measurements revealed another anomaly. When light scatters off cometary dust, it becomes partially polarized. The degree and angle of polarization revealed dust properties. 3. I-Atlas dust, polarized light in the opposite direction from normal. Negative polarization, unprecedented for interstellar objects, indicating particle properties completely unlike solar system comet dust. Each anomaly individually might be explained. Unusual composition, atypical structure, specific viewing geometry. But collectively, the anomalies created a profile that didn't match any known category. 3. I-Atlas wasn't behaving like solar system comets. It wasn't behaving like previous interstellar visitors. It was unique, unexplainable within existing frameworks. And then came the alert that changed everything. Comment below. What would you do if an interstellar visitor suddenly broke all the rules? November 1st, 2025. Mark this date. This is when 3 I-Atlas crossed from unusual to impossible. NASA's Neil Gehrels Swift Observatory was conducting routine monitoring of 3 I-Atlas position. Swift, designed primarily to detect gamma-ray bursts from distant galaxies, carries ultraviolet and optical instruments capable of observing comets. It had been tracking 3 I-Atlas for weeks, measuring hydroxyl emission as a proxy for water sublimation. Hydroxyl radicals, chemical formula OH, are created when solar ultraviolet radiation breaks apart water molecules. Detecting hydroxyl emission tells you water is sublimating and being photodissociated. The strength of hydroxyl emission correlates with water production rate. This is standard cometary observation technique, reliable, used successfully on thousands of comets. Swift's latest scan showed hydroxyl emission had intensified, not slightly, dramatically. The signal strength indicated water vapor release rates that exceeded previous measurements by substantial factors. The Swift team's first reaction was to suspect instrumental problems. They checked calibration, verified pointing accuracy, compared current readings to reference stars with known ultraviolet brightness. Every diagnostic confirmed the instruments were functioning correctly. The hydroxyl signal from 3 I-Atlas was genuinely that strong. But here's the problem that stopped everyone cold. 3. I-Atlas was currently located at 3.1 astronomical units from the Sunday. At that distance, surface temperatures should be around -150 degrees Celsius. Water ice doesn't sublimate significantly at those temperatures. Carbon dioxide, yes. Carbon monoxide, definitely. But water should be largely dormant. Yet, Swift detected strong hydroxyl emission indicating vigorous water sublimation. And more concerning, the emission had intensified compared to previous observations taken when the comet was closer to the Sun and receiving more solar radiation. This is backwards, completely backwards. Cometary activity should decline as objects move farther from the Sun and cool down. 3 I-Atlas activity was increasing as it receded and cooled. This violates thermodynamics at the most basic level. Objects don't spontaneously increase temperature when they move away from heat sources. Heat flows from hot to cold, never the reverse. This is fundamental physics. Within hours of confirming the measurements, NASA issued the priority alert, not a routine notification. A priority alert acknowledging that what multiple instruments were measuring couldn't be explained by existing theoretical frameworks. Hubble Space Telescope received targeting instructions. Ground-based observatories in Chile, Spain, Hawaii, and Australia were notified. The James Webb Space Telescope observation schedule was adjusted. Maximum resources were being directed at understanding what was happening. because if the SWIFT measurements were accurate, if hydroxyl emission was genuinely intensifying as 3I Atlas receded from the Sun, then something was providing energy beyond solar heating. Some internal process, some chemical reaction, some mechanism not accounted for in any cometary model ever built. The global astronomy community responded immediately. This is what priority alerts do. They mobilize coordinated international observation campaigns. They ensure that every instrument capable of contributing data is pointed at the target. Subscribe now, because what these instruments discovered next confirm that 3I Atlas isn't just unusual, it's forcing fundamental revision of how we think about cometary activity. 48 hours after the SWIFT alert, Hubble Space Telescope's Wide Field Camera 3 locked on to 3I Atlas. Hubble's capabilities complement SWIFT's. While SWIFT excels at ultraviolet observation, Hubble provides high-resolution imaging across ultraviolet, visible, and near-infrared wavelengths. The imaging sequence targeted specific features, the jet structures that previous observations had documented, the coma morphology, the dust distribution, polarization properties through specialized filters. Each image would add data about what was physically happening as the comet's activity unexpectedly intensified. When the data arrived at the Space Telescope Science Institute in Baltimore, researchers opened the files expecting to see the familiar jet structures documented weeks earlier. What appeared on their monitors stopped conversations mid-sentence. The jets had changed, not slightly, dramatically. The column of material erupting from the nucleus had brightened substantially. More gas and dust was being released. The coma had expanded. And this wasn't gradual evolution. This was rapid transformation occurring as the comet moved farther from the Sun into colder regions where activity should be declining. One researcher later described it as watching ice cream melt while you put it back in the freezer. The analogy is perfect. You don't expect increasing activity when conditions favor decreasing activity, yet that's exactly what Hubble imaged. The intensity increase wasn't uniform across the coma. Specific jet sources had brightened more than others. This suggested localized processes. Particular regions of the nucleus were more active. Perhaps those regions had composition or structure different from surrounding areas. Perhaps subsurface reservoirs were venting through specific pathways. Perhaps fracturing had exposed fresh, volatile deposits. But here's what made this observation crucial. Hubble's independent detection of jets intensifying while the comet receded from the Sun eliminated any doubt that Swift's measurements might be instrumental artifacts. Multiple instruments on different platforms were measuring the same phenomenon. 3I Atlas activity was increasing despite moving into conditions where decrease was predicted. This meant something was providing energy beyond solar heating, some internal source, some process not included in standard thermal models. Hubble's polarization filters added another layer of mystery. The negative polarization observed earlier had increased in magnitude. The angle had shifted deeper into negative territory. Now measuring negative 18 degrees, confirmed independently by ground-based polarimetry from the European Southern Observatory's Very Large Telescope in Chile. This polarization behavior indicates dust with properties astronomers have never measured in any other comet. The particles must be extraordinarily small, perhaps nanometer scale, or they must have compositions that interact with light in fundamentally unusual ways. Either explanation suggests 3I Atlas dust formed under radiation and chemical conditions completely unlike those that produce solar system comet dust. The James Webb Space Telescope brings capabilities that neither Swift nor Hubble possess. Webb operates primarily in infrared wavelengths. Its spectrometer can analyze molecular emissions invisible to optical instruments. Its sensitivity allows detection of species present in small abundances that other telescopes might miss. Webb's spectroscopic observations of 3I Atlas aim to answer a crucial question: what molecules are being released? The hydroxyl emission that SWIFT detected comes from water dissociation. But what else is sublimating? What's the complete chemical inventory? The resulting spectrum confirmed the carbon dioxide dominance that earlier observations had suggested. The ratio of carbon dioxide to water was approximately 8:1, completely inverted from typical solar system comets, where water dominates by similar factors over carbon dioxide. This inverted ratio explains some of 3I Atlas behavior. Carbon dioxide sublimates at much lower temperatures than water. At 3 astronomical units, surface temperatures might be insufficient for vigorous water sublimation, but perfectly adequate for carbon dioxide. If the comet is carbon dioxide rich, sustained activity at large solar distances becomes explainable. But Webb detected something else, an absorption feature at 4.5 micrometers that doesn't match any known cometary molecule, not water, not carbon dioxide, not carbon monoxide, methane, ammonia, or any cataloged volatile. An unidentified compound producing a clear, repeatable spectral signature that appears in every observation. This unknown compound might be the key to understanding 3I Atlas anomalous behavior. If it's a molecule that releases energy when it transitions between states, if it undergoes exothermic reactions that generate heat, it could provide the missing energy source that thermodynamic calculations require. But identifying the compound is proving difficult. Spectral databases contain thousands of molecular signatures. None match the observed feature precisely. This suggests either a molecule that hasn't been synthesized and characterized in laboratories, or a known molecule behaving differently under the extreme conditions in the comet's coma. Research groups are currently working through possibilities, trying different chemical species, modeling how known molecules might produce the observed feature if they exist in unusual environments, testing whether mixtures of multiple species could create the composite signature. This analysis takes time, months potentially. The spectrum is data. Interpretation requires exhaustive comparison with theoretical predictions. What makes this significant isn't just that an unknown compound exists. It's that this compound appears to correlate with the activity intensification. Webb's observations show the 4.5 micrometer feature strengthens in parallel with the overall outgassing increase. Whatever this molecule is, it's involved in the process driving 3I Atlas to behave in ways that violate standard predictions. And if this compound is something that only forms under specific stellar conditions, if it's a signature of the stellar environment where 3I Atlas originated, then identifying it tells us about that environment, about the star system that created this comet, about conditions around other stars that produce chemistry we don't encounter in objects that formed around our sun. While space-based telescopes tracked chemistry, ground-based observatories focused on dust properties, because 3I Atlas dust is doing something that standard physics says is impossible. The European Southern Observatory's Very Large Telescope in Chile deployed its SPHERE instrument for polarimetric analysis. Polarimetry measures how light's electric field vector rotates when it scatters off particles. Different particle sizes, shapes, and compositions produce different polarization patterns. By measuring these patterns precisely, astronomers infer physical properties of dust they cannot directly observe. For 3I Atlas, polarimetry has revealed the most anomalous dust properties ever measured in a comet. The negative polarization is unprecedented. Standard scattering theory, developed over centuries and tested on millions of objects, predicts positive polarization for typical cometary dust. Light scattered by particles comparable in size to visible wavelengths should have its electric field vector rotated in specific directions. 3I Atlas dust rotates the field in the opposite direction. This requires either extraordinarily small particles or exotic compositions. Nanoparticles, grains smaller than the wavelength of light, can produce anomalous scattering, including negative polarization. But creating abundant nanoparticles requires specific processes. Normal sublimation doesn't produce them. They might form through condensation of vapor in the coma. They might result from shattering of larger grains through collisions or radiation pressure. Alternatively, the dust might have compositions with optical properties completely unlike silicates and carbonaceous materials that dominate solar system comet dust. If 3I Atlas formed in a carbon-rich, oxygen-poor environment, its dust might consist primarily of carbon compounds with different refractive indices and absorption properties. These materials could scatter light in ways that produce the observed negative polarization. The polarization magnitude has been increasing as activity intensifies. Early measurements showed slight negative values. Current measurements show negative 18 degrees. This evolution suggests either that dust properties are changing as activity intensifies, or that different dust components dominate at different times. The Very Large Telescope observations have been complemented by Hubble polarimetry and by ground-based instruments in Hawaii and the Canary Islands. All independent measurements confirm the negative polarization. This isn't measurement artifact. Multiple facilities using different instruments and different calibration procedures all report the same result. And that result tells us 3I Atlas dust is fundamentally different from any dust astronomers have characterized before. It formed under conditions unlike those in our protoplanetary disk. It was processed by radiation from a star with different spectrum than our Sunday. It carries information about stellar environments we cannot directly observe encoded in its physical properties. Let's address the central problem directly. The observation that forced NASA to issue priority alerts. The measurement that has scientists genuinely puzzled. 3. I-Atlas is currently 3.1 astronomical units from the Sunday. At that distance, solar flux is approximately 9% of what Earth receives. Surface temperatures, assuming standard thermal properties, should be around negative 150 degrees Celsius. At negative 150 degrees Celsius, water ice does not sublimate significantly. The vapor pressure is too low. Molecules don't have sufficient thermal energy to escape the ice lattice. Water activity should be minimal, dormant, nearly zero. Carbon dioxide ice begins sublimating around negative 78 degrees Celsius at low pressure. Even that temperature isn't reached at 3.1 astronomical units given standard thermal models. Yes, carbon dioxide is more volatile than water. Yes, it remains active at colder temperatures. But even carbon dioxide should be largely dormant at this distance. Yet observations show vigorous outgassing, tens of kilograms of material being released per second, hydroxyl emission indicating water sublimation, dust production creating an expanding coma, jets brightening rather than fading. This activity requires energy. Sublimation is an endothermic process. It consumes energy. The latent heat of vaporization must be supplied to transition ice from solid to gas. That energy has to come from somewhere. Solar radiation provides 9% of Earth flux. Scientists have done the calculations. They're straightforward. Input the solar flux. Apply it to the estimated surface area. Account for albedo. Calculate how much ice can sublimate. The numbers don't work. The solar energy input cannot drive the observed outgassing rates. It's insufficient by orders of magnitude. So where is the energy coming from? Possibility 1, internal radioactive decay. Some isotopes generate heat through radioactive decay. If 3I Atlas nucleus contains substantial quantities of these isotopes, internal heat generation might supplement solar heating. But this requires specific isotopes in high concentrations, and those isotopes have finite half-lives. Over billions of years, they decay. By now, most radioactive heat sources should be depleted. Possibility 2, exothermic chemical reactions. Perhaps the unknown compound Webb detected participates in reactions that release energy. Chemical energy, not just phase transition from solid to gas. If the compound releases heat when it reacts or transitions, that heat could drive additional sublimation. But this requires specific chemistry, and that chemistry must release energy at rates matching observations. Possibility 3, subsurface pressure. Perhaps internal voids contain volatiles under pressure. As solar heating penetrates, these reservoirs vent. Pressure release does work, converting stored pressure energy into kinetic energy of escaping gas. But pressure venting should be episodic. Brief outbursts, not sustained intensification over weeks. Possibility 4, something we haven't considered. Some mechanism or process that operates in interstellar objects but hasn't been observed in solar system comets. Some physics that's possible but hasn't occurred in our experience. Scientists are currently working through these possibilities systematically, testing each against observations, trying to determine which, if any, explains the energy budget problem, or whether multiple mechanisms operate simultaneously. The answer matters beyond just 3I Atlas. If comets can have internal energy sources that dominate over solar heating, models need fundamental revision. Our ability to forecast behavior diminishes. Every future interstellar visitor might require individual analysis rather than application of standard models. Overlying the steady background mystery of increasing activity is another anomaly that has observers stunned: brightness fluctuations. 3I Atlas doesn't glow steadily like normal comets. It flares. Explosive brightenings, appearing without warning, peaking in hours, fading over days. These outbursts occur unpredictably. No obvious periodicity, no correlation with rotation that might indicate specific active regions coming into sunlight as the nucleus spins. No clear relationship to solar distance. They just happen, suddenly, without warning. Cometary outbursts aren't unprecedented. Many solar system comets show similar behavior. But typically, outbursts occur closer to the sun where solar heating is intense, and they usually result from specific triggers: surface crust fracturing, sublimation of buried hypervolatile deposits, collapse of subsurface cavities. 3I Atlas outbursts are happening at 3 astronomical units where temperatures shouldn't allow the dramatic sublimation that drives outbursts. The thermal environment seems wrong for this behavior, yet it occurs repeatedly with increasing frequency as overall activity intensifies. Ground-based monitoring has captured some outbursts in real time. Brightness increasing by factors of 2 to 3 over hours, then declining over days. The rapid rise suggests sudden gas release. The gradual decline suggests expanding material slowly dispersing. But what triggers these events? At the temperatures present, what causes sudden venting? Each hypothesis has problems. Temperature variations as the nucleus rotates. Doesn't fit outbursts don't correlate with rotation period. Subsurface pressure buildups? Possible. But why would thresholds be reached randomly? Impacts from debris? Unlikely at observed frequencies. And here's the pattern that is scientists most concerned. Outburst frequency is increasing. More eruptions per week than in previous months, as if whatever internal process drives them is accelerating, as if the nucleus is becoming more unstable, or as if the energy source powering 3I Atlas is ramping up, getting stronger, driving more vigorous activity, including these explosive venting events. Amateur astronomers worldwide have joined professional monitoring programs. Thousands of enthusiasts with telescopes capable of imaging 3I Atlas. Their observations provide continuous coverage that professionals cannot match. When outbursts occur between scheduled professional observations, amateurs catch them. Data gets posted online. Professionals are notified. Follow-up spectroscopy gets scheduled. This global collaboration is capturing an unprecedented dataset. Every outburst documented, brightness evolution tracked, the pattern or lack of pattern being characterized in detail. A fortunate orbital coincidence is about to provide unprecedented opportunity. NASA's Europa Clipper mission, launched to study Jupiter's ice-covered moon Europa, is currently traveling outward from Earth on its multi-year journey to the Jovian system. Europa Clipper's trajectory was calculated years ago based on orbital mechanics and mission requirements: launch windows, gravitational assists, optimal arrival time at Jupiter. None of that planning considered 3I Atlas. because this comet wasn't discovered until 2025, and Clipper launched earlier. But orbital mechanics doesn't care about planning. Objects follow paths determined by gravity, and Europa Clipper's path happens to intersect regions of space where 3I Atlas has deposited material. As the comet releases gas and dust, that material doesn't stay with the nucleus. Solar radiation pressure pushes dust outward. Solar wind drags ionized gas. Molecules and particles spread across millions of kilometers, creating a dispersed tail and trail that marks where the comet has traveled. Europa Clipper will pass through this dispersed material. The spacecraft carries instruments designed to study particles and plasma around Jupiter. Those same instruments can sample interstellar material from 3I Atlas, not remotely, directly. Particles will impact detectors. Ions will trigger sensors. Actual physical samples of interstellar material will be measured. This is unprecedented in human history. Previous interstellar objects were studied entirely through remote sensing. Telescopes measuring light, spectroscopy inferring composition, everything indirect. Europa Clipper will collect direct samples, particles from another star system measured with laboratory-quality instruments. The spacecraft's surface dust analyzer can determine composition of individual dust grains, mass spectrometry identifying elements and isotopes. The plasma instrument measures charge states and densities of ions. Together, these instruments will characterize 3I Atlas material far more precisely than remote observation allows. Isotopic ratios are particularly valuable. Different stellar environments produce different isotope abundances. Measuring oxygen isotopes, carbon isotopes, nitrogen isotopes in 3I Atlas particles directly constrains where in the galaxy it formed. Was the parent star metal-rich, metal-poor, young, old? Isotopes encode this information. Mission controllers have coordinated with NASA's Heliophysics Division to ensure all relevant instruments activate during the passage. The encounter won't last long, hours at most. But during that window, Europa Clipper becomes humanity's first interstellar dust collector. Results won't be immediate. Data will be transmitted to Earth. Analysis will take months. But eventually, papers will publish the first direct measurements of interstellar material. And those measurements might finally explain what makes 3I Atlas so unusual. Or the mystery might deepen further. Because every time scientists get closer to 3I Atlas, the object becomes stranger rather than more familiar. What could direct sampling teach us that telescopes cannot? 3 interstellar objects have visited us, each one completely different, each one breaking different rules. The pattern reveals something profound about cosmic diversity. One-eye Oumuamua arrived in October 2017. Pan-STARRS in Hawaii detected it as it was already leaving the inner solar system. By the time astronomers recognized its interstellar origin, it was already receding. Observation time was limited. Oumuamua showed no cometary activity whatsoever. No coma, no tail, no detectable outgassing. It appeared completely inert, just a tumbling rock passing through. Its brightness variation suggested an elongated shape, possibly 10 times longer than wide. But no gas or dust was observed. Yet Oumuamua showed non-gravitational acceleration. Its trajectory deviated slightly from pure gravitational predictions. Comets show this regularly from outgassing rocket effect. But Oumuamua had no visible outgassing. This created intense debate that remains unresolved. Some scientists proposed invisible hydrogen sublimation. Others suggested exotic explanations. The mystery persists because Oumuamua faded beyond detection before definitive measurements could be made. 2I. Borisov arrived in August 2019. Amateur astronomer Gennady Borisov in Crimea discovered it while it was still approaching. This provided much more observation time than Oumuamua. Borisov behaved conventionally. Clear cometary activity. Water vapor and carbon monoxide detected spectroscopically. Dust tail developing. everything following standard cometary physics. The composition matched solar system comets. Water dominated, activity onset, brightness, evolution, everything predictable. Borisov was reassuring. It proved that some interstellar comets form through processes similar to our solar system's comet formation, that our physics applies to at least some objects from beyond. Now, 3, I-Atlas. And it's neither inactive like Oumuamua nor conventional like Borisov. It's active, showing clear cometary behavior, but that behavior doesn't match predictions. Chemistry inverted, thermal response contradicting models, brightness fluctuating inexplicably, dust properties impossible for standard materials. 3 objects, 3 completely different profiles. What does this tell us? That interstellar objects span enormous diversity. Formation around different stars, under different conditions, produces objects with wildly different properties. Our solar system's objects don't represent universal standards. Each visitor requires individual analysis because applying standard models fails. Do interstellar objects follow any predictable rules at all? Here's the uncomfortable truth scientists are confronting. Everything astronomers thought they understood about comets was built on studying thousands of objects, all formed around our Sunday. Models work beautifully for those objects. Brightness predictions, activity models, chemical compositions. Then 3i Atlas arrives, and every model fails. This failure reveals something crucial. Our models aren't universal, they're local. They describe our neighborhood, apply them elsewhere, and predictions collapse. This isn't a failure of science. This is science working exactly as designed. Models built on limited data sets eventually encounter phenomena outside their validity. When that happens, when observations exceed predictions, the scientific method demands model revision. Not defending old models stubbornly, adapting, expanding frameworks, building better theories that accommodate both familiar local objects and exotic interstellar visitors. 3, I-Atlas is forcing this expansion. Every measurement that contradicts predictions is information. Every behavior that violates models is a clue about what's missing from those models. Science improves by being wrong, by making predictions that fail, by acknowledging failure and building better frameworks. 3, I-Atlas is making science better by demonstrating limitations of current understanding. This is uncomfortable. Scientists prefer confirmation to contradiction, but contradiction drives progress. Every major advancement in science came from observations that contradicted prevailing theories. 3, I-Atlas might be such a phenomenon, revolutionary in expanding our understanding of cometary diversity, chemical possibilities, and the range of outcomes stellar environments produce. Step back. See what 3 I-Atlas really teaches about the universe. We've studied our solar system comprehensively, mapped every planet, characterized thousands of asteroids, tracked hundreds of comets, built comprehensive theories explaining formation and evolution. Those theories work beautifully for local objects. But the solar system represents one outcome of one set of initial conditions, one stellar mass, one chemical composition, one formation environment. Other stellar systems formed under different conditions, different masses, different chemistry, different radiation. Those differences produce different outcomes. 3 I-Atlas provides direct evidence of this diversity. It's a comet from elsewhere, formed under conditions unlike ours. Its chemistry reflects those differences. Its behavior reveals that processes we thought universal actually depend on context. This has profound implications for exoplanet science. We're discovering thousands of planets around other stars, trying to understand them using frameworks based on solar system examples. But if those planets formed under different conditions, our frameworks might fail. Just as cometary models failed for 3 I-Atlas, planetary models might fail for exoplanets. Science must expand, must accommodate diversity, must recognize that studying one stellar system doesn't prepare us for understanding the full range of outcomes nature produces. As this recording ends, 3I Atlas continues outbound from the Sunday, still releasing material at impossible rates, still displaying inverted chemistry, still polarizing light in directions that violate theory, still erupting without pattern or explanation. NASA's alert remains active. Telescopes worldwide continue their vigil. Scientists work to extract meaning from measurements that challenge everything they thought they understood. This visitor traveled incomprehensible distances to reach us, millions of years in the darkness between stars, carrying messages about stellar environments we cannot visit, chemistry we haven't synthesized, processes we haven't observed. The energy source remains mysterious, the unknown compound unidentified, the dust properties unexplained. But every observation constrains possibilities. Every measurement narrows the solution space. Eventually, explanations will emerge that fit all data consistently. Those explanations will improve understanding not just of 3I Atlas, but of comets throughout the galaxy, of how stellar diversity produces cometary diversity, of what physics we haven't encountered because our sampling was too limited. 3I Atlas stunned NASA and Harvard, continues stunning everyone studying it, and will likely provide surprises until it fades completely from detection. But the data persists. Papers will emerge for years analyzing specific aspects. Models will incorporate lessons learned. And when the next interstellar visitor arrives, we'll be better prepared. Each visitor teaches. Each observation pushes boundaries. 3I Atlas is doing exactly that, pushing hard, challenging fundamentally, forcing science to grow. And growth, even when uncomfortable, even when it means admitting previous certainty was premature, is what science exists to achieve. Better understanding, deeper knowledge, closer approximation to truth about the universe we inhabit. 3I Atlas is helping us reach that truth, one impossible observation at a time. The mysteries continue, the data accumulates, and somewhere in the spectral lines and polarization measurements and brightness curves, the answers wait to be found. Comment below, what do you think 3I Atlas will teach us next? Subscribe, because this story isn't over. Europa Clipper approaches. Analysis deepens. And as scientists work to decode this visitor's secrets, we'll bring you every discovery, every insight about this ancient traveler, showing us just how much we still need to learn. The universe is stranger than we imagined. 3I Atlas is the proof. Our comprehensive understanding was never comprehensive. It was local, limited, built on narrow experience. The galaxy is vast, diverse, full of phenomena we haven't encountered, and sometimes those phenomena come to us, messengers from the cosmic wilderness, carrying truths that challenge everything we thought we knew. 3I Atlas is one such messenger, and its message is being received.